Good evening, everyone. Welcome to 12th live session of Vigyan Charcha Asur. Vigyan Charcha Asur works to promote scientific awareness among everyone, especially with students. Today is a special day for Vigyan Charcha Asur because today we have someone who works with CERN for around 50 years. So it's an opportunate time for us, and we will know about God particle from horse mouth. From today, I welcome Sananda Banerjee. So Sananda Babu has a really great career. He is linked with Sun for more than 50 years. He first joined Sun as a student on 70s, and then he worked with Sun in different capacities. Uh, in 70s, he joined the Imperial College London. Then from 77, he started working with TFR, first with as a visiting fellow, and then as a reader, associate professor, and different. He took different role, and he also worked with Sam. He worked as a project associate, then paid associate, and other roles. He worked with the Fermi National Accelerator also, and then he worked with Saha Institute of Nuclear Physics as a professor. And he also worked with Fermi National Accelerator, University of Wisconsin, and presently he is working with Indian Association for the Cultivation of Science, Kolkata, as its senior scientist. So really, it's a glorious career. He received many awards. I'll just mention a few of them. Like last year, he received the Breakthrough Prize in Fundamental Physics. He's also received the Lifetime Award from the CMS Experiment at CERN, Geneva. He is fellow of West Bengal Academy of Science and Technology, Kolkata. He is fellow of Indian National Science Academy, New Delhi. He is fellow of Indian Academy of Science, Bangalore. So really glorious career. So I'll not take more time, and I'll request Sananda Babu to take stage and say something about the God's particle.
Good evening, everyone. It was a pleasure for me to be at in this particular program. In fact, about a year ago, Sananda invited me to become a member of this particular group. I have been a member, but a silent member of this group for about a year, and she has asked me to talk about something. I think this is a thing. And she also asked me if I can say my connection with this particular discovery and how I came to know about particle physics. And so I'll be talking about not just Higgs boson, but also how step by step we came to know more and more about particle physics as such. So let me start about this. And sorry. Now, how science advances? We start with what we already know. So we already have some prejudices which we try to preserve, like we assume isotropy in space and time, and this leads to some conservation principles like momentum, energy, etc. We believe that the laws at low energies when properly computed, will not violate the principle of probability at high energies. That means probability of happening will remain finite in all orders of perturbation theory. So with these ideas, okay, we proceed, okay, with starting from the things. And in fact, okay, the field in which I work not just started as such, okay, it started in the field of philosophy. I think both in the Western world as well as in the Eastern world, people were really thinking, okay, what everything has been built of, and they have some ideas, but it was not all scientific. I think in modern science started around the 16th century, and there any postulation needed an experimental verification. I have put a picture of Galileo Galilei in this slide, and he made this famous statement, I attach more value to finding a fact, even about the slightest thing, than to long disputation about the greatest question that failed to lead to any truth whatsoever. That means, okay, whenever we made a postulate, we try to find out some way by which we can verify it, and that means, okay, it has to be done through certain experimentation. So any postulation has to go hand in hand with some finding by which you can either support that postulation or nullify the postulation altogether. So any theory which cannot be verified through experiments is still not a pure scientific theory as such. So how did I advance in this particular field? I started learning during the 60s and early 70s in Calcutta. West Bengal at the time was going through acute food crisis. You people may or may not be aware of what was happening. The government was run by Congress, and they had crumbling, and the left movement was starting up at that time. So when I went to college, the Nongshar movement was in full swing. So that was one of the things which I was facing at that time. The second thing is that, okay, I mean, computers were considered evil to the society. It was trying to take away the jobs of people. So obviously, okay, I mean, computers is a no-go, okay, I mean, completely. Okay, I mean, so I mean, we only talk about computers in the newspapers, and we never learned anything when we are either in the school or in the college. The other thing, okay, where I studied, okay, the college remained closed for years, and examinations were delayed by 6 months to a year. But even under that circumstances, I was lucky in many ways. First of all, okay, the general line was considered to be the best profession ahead of any technical line, like being a doctor or an engineer. So most of the people who did well in the schools, I mean, they were going to study in general line, either in science or in humanities or in commerce. Okay, but they're all going in the general line whatsoever. And there are very few people, okay, went to a technical line at that time. Okay, and obviously, as I said, okay, computer was a no-go, okay, completely at that time. And it happened that I went to a Bengali medium school, and I met a school teacher who was not even a matriculate, and he advised two things, which really framed the way, okay, I mean, I try to do all my future work. He was essentially talking in the context of copying in the examination. He said if one remembers the content from any book and reproduces that in the examination paper, it is as good as copying the things, okay, in the examination hall. So this thing has been stuck in my mind, okay, forever. So I never tried to remember things. Anyway, my memory is not very good, so it helped me quite a lot. I don't want to try to remember anything from the book. I only try to understand what is lying in the book itself, and I could really work out in an examination hall, starting from the first principles. So this has helped me in my college quite a lot, because in the college where I studied, most of the examinations were on problems. So I think problems were, anyway, we came to know the problems only when in the examination hall, and we could solve it out. But the university examination was not like that. In university examination, they're trying to say, okay, I mean, you have to give how a particular experiment is done. Now, I knew, okay, I mean, that particular experiment was basically trying to measure the thermal conductivity of the things. So from my ideas, okay, I mean, how an experiment could be done, I could think about that in the examination hall and try to work out what are the things which it could be said as a precaution, how to do, not so that they can get a reasonable result out of it. I could work that out and try to write down in the paper. Obviously, this will not give me high marks. Okay, this was not something which was written in any book. It came from my head and in the examination hall itself. But this is a thing, okay, which I lived with, okay, through my entire life. I never try to remember things, but I try to work out from the first principles. Even when I'm is not a theoretician, but an experimentalist. So that was the first thing, okay, which I learned, which was in my early days, and this was a really great thing, okay, which I would say, okay, I mean, which has really shaped my life in the future. The second thing is that getting the possibility of doing physics honors in Presidency College would be the best choice for a future career. This was what my teacher told me at that time, and I got a chance for doing that, and that really led my future career all the way through. The third thing where I was lucky, I would say, the government gave me a generous amount through which I could attend a summer school in Chandigarh when I was in my first year in the college. And that gave me the chance to have a glimpse of a computer for the first time. And that is from a distance and not really knowing, okay, what exactly a computer can do. Now with that, okay, I mean, I come to my next steps, okay, I mean, what is done. When the college remained closed, after only 1 month of a class in my third year, all students in our class were ready to get out of Calcutta. I was one of them. My first attempt was to go to Delhi. It did not work out for some reasons. Okay, I mean, some of my friends could go, okay, but I could not go. But I got a chance to go to Imperial College London to be admitted in experimental particle physics. Now, this particular thing, okay, I mean, was disliked by my teachers because they were unhappy that they thought that I would be doing better in theory, not in experiments. But it also, I was not too happy about this because I did not know many things in physics. I did not know anything about quantum mechanics and not much about mathematical methods at that time. So I was very, very much afraid of what I should do. So I approached a professor in Calcutta University, physics department, and he did his PhD from Imperial College itself under a very renowned physicist, and he asked me to use some of the stipends which I received to buy a few books. So these are the books he suggested. He suggested 4 books of Landau-Lifshitz, the book of Quantum Mechanics by Paul Dirac, and a Mathematical Methods by Dennery. So I learned my quantum mechanics by reading the book of Dirac. So I know, well, I think, I mean, obviously the book of Dirac is not the best book to learn quantum mechanics, but it gave me some idea, okay, about the philosophy of quantum mechanics, okay, at that time. And I really loved it, okay, I mean, I would say. I spent several months trying to learn by myself with some help from the professor. So I bunked my MSc class, okay, after attending maybe a couple of months and tried my luck in an unknown university in an unfriendly place like UK. So I realized, the first thing I said, I realized how much deficit I had after facing the faculties at Imperial College. So that they suggested me to go through several lectures from the experimental high energy physics group. They provided me 6 sets of lectures on experimental techniques, accelerators and detectors, basic relativistic kinematics, using of quantum mechanics in the analysis, dynamics in high energy interaction. So this was the thing which the experimental group provided me. Then the theory physics group suggested me with 4 sets of lecture series. S-matrix theory, this was a theory for strong interaction in those days. Quantum field theory, group theory, and regipole theory. In addition, I had to take 2 more courses from the undergraduate school, one on quantum mechanics and one was computer programming. Now, Imperial College had an excellent lecturers in high energy physics, both theory and experiments. You may know some of the names. One was Paul Matthews, Abdul Salam, Tom Peebles, Bob Delburger. These are all theorists. And then you have, among experimentalists, I just named 2 of them, Ian Butterworth and Peter Donan. So apart from these 13 courses and hundreds of problem sheets, there were loneliness in personal life, but 3 things kept me alive. I used to get a letter from my mother every day. I mean, she used to write a letter without thinking for a return reply. So that was something which she kept on doing for 3 years. Then we had regular visits from my uncle and cousins who were at that time in UK. And my uncle, he's talking about, he was the first cousin of my father, and he was also a first cousin of Satyajit Ray. So meeting, and the third thing which really helped me, I met my college hero. I am not talking about who it was, who also came to UK for doing his PhD. Okay, so obviously he was much senior to me, at least 8 to 10 years senior to me. But he was my college hero, okay, for, I wouldn't say why, but I used to really had a very high opinion about him. Anyway, I was alive after a year, and I was told I have done reasonably well in that 1 year. So I could be doing my PhD from at the age of 20. So that was the thing which I had to do. So till the end, now I come to the situation of high energy physics at that time. Now till the end of the 19th century, the search was done to look at the fundamentals of the things was mostly in the domain of chemistry. The idea of compounds and elements was there. There was a classification of elements in a periodic table and the idea of molecules and atoms. Now, at the end of the 19th century and the beginning of 20th century, there was a conclusion that all matters are built of electrically neutral units, atoms of several fundamental elements. On the physics front, the investigation was on the types of interactions among matters, and there were 2 types of interactions which were seen. One was due to Newton, essentially due to Newton, the gravitational interaction between any 2 objects having mass. And obviously there's many others who contributed to that, but I think, okay, then the Newtonian mechanics, okay, I mean, is one of Newtonian theory of gravitational is one of the leading things at that time. And then it was due to Maxwell of electromagnetic interactions. But there was a revolution around the corner, okay, at that time, and it came through the essentially experiments done in France and Britain, and this was talked about the idea that there were two other interactions which were there. One was interactions between, you have the idea of nucleus, so there was a strong interaction, and then there was a radioactivity, okay, and then it was a weak interaction. So during the 20th century, with the discovery of accelerators and many modern techniques of detecting basic constituents and their interactions, people came up with the idea of a new zoo of fundamental constituents. There was a group of spin half particles exhibiting Fermi-Dirac statistics, which make up all the constituents of matter, which are called fermions. And these particles interact among themselves to the exchange of some spin-1 objects exhibiting different statistics, which was due to Bosch and Einstein, which is called bosons. So apart from gravitational interaction, there are three types of interaction which is there. Weak interactions, electromagnetic interactions, and strong interactions. And they can all be explained through quantum field theory. And this gave birth to the standard model. And this model has, what do you call it? I can't see. Has gone through several tests at that time. Now, the decade of the 60s ended with a lot of promises in the field of high energy physics. We had a discovery of a large number of hadrons, that means which exhibit strong interactions. And that led to the idea that these hadrons are not fundamental particles, but made of more fundamental constituents. And Gell-Mann came up with the idea of quarks. Gell-Mann and Zweig, okay, when they came up with the idea of quarks for that. Then there were experiments which were done by probing protons with electrons and gave evidence of point-like constituents within protons. This was very similar to Rutherford experiment, okay, when we talked about that the idea of nucleus. And obviously that it had inside the thing, okay, this is the thing, okay, I mean, Feynman said, okay, I mean, the protons has got partons. Obviously, okay, there were quarks on one side and partons on the other side, and then at some point in time, okay, I mean, they said, okay, I mean, partons have quarks, and also something which glues quarks together, which is called gluons. Now, theories of electromagnetic and weak interactions were so similar that there was a possibility of having a unified theory of these interactions. But at that time, when I was a student, there were several ways to unify them, and each needing the existence of some yet to be discovered particle. And there were many symmetries which are found to be exact, okay, like I have already talked about the translation and rotation and all these things which are there, okay. There are many other symmetries for internal symmetries, but there were some which were not violated by a tiny amount. Now, these quarks and leptons were the things, okay, like electrons and neutrinos. They're found in 2 generations, but there are 4 types of leptons and only 3 types of quarks. Now, the way to move forward was to make use of new experiments and observations. And obviously, when you want to do new experiments, okay, I mean, and you need, okay, I mean, how you can do these experiments. Obviously, you have to make your experimental instruments by yourselves, and this is how the thing started in the beginning of 1970s. To move forward, the experiment technology has to advance. First of all, you have to probe at shorter distance. That means you have to really utilize very high energy probe. I mean, that means, okay, very high frequency photon, or you can use, okay, I mean, even particles which are accelerated to very high energies. And it started with accelerators to start with, but then you really, when you want to go up in energy, okay, I mean, you have to think about colliding highly energetic particles. Like you have a collision between electrons and positrons. So they came up with the idea of a E plus E minus collider. And the first one was built in Italy called ADA. And similarly with a proton-proton collider, ISR at CERN. Both these things happened in the 60s. The second thing is to observe rare events. When you the idea is that when you have a bulk thing which you are seeing, okay, that is first of all explained away. Then if you want to see much more interior, you have to really see rarer and rarer things, okay, to understand more and more about how the things develop. So you move away from visual detection techniques to electronic devices. Previously, okay, we are using detection techniques like immersion plates, or something which we talked about, like a bubble chamber or a cloud chamber. But we have to use these things, we have to use the electronic devices for doing that. And obviously, okay, if you want to have a rare events, okay, I mean, you have to produce intense beams of particles by devising new focusing techniques. Now, the indirect observation of a new phenomena needs experiments with a higher precision. So use new experimental techniques in data collection and analysis. And this basically you use detectors of different types. Then you need observations. That means you do not observe all the things which is of no interest to you, but you observe events which are of interest to you. That means you trigger some of the things which you try to observe. And then you have to really testify that whatever you are doing in a complex detection techniques by using simulation and visualization. And obviously, the last thing comes, try to employ artificial intelligence. Now, I must name two eminent persons, okay, I mean, who worked in these fields of accelerators and detector technologies. And with their help, okay, I mean, things really moved. The first figure is the picture of Simon van der Meer. He improved how intense neutrino beams can be produced, which is called using magnetic horn, or how you can cool down antiprotons, okay, through a stochastic cooling, okay, to make a antiproton-proton collider. The other person I am talking about is the second person is George Charpak. He has devised newer and newer detection techniques, okay, by evolutionaries, okay, all the detection techniques which is there. So with these things, okay, one can really move forward in doing experiments. The first thing which happened, I would say, okay, when one tried to unify the electromagnetic and weak interactions, it needed the existence of a new particle. Either it could be a heavy charged lepton, This was coming from a theory of Georgi and Glashow, and or a neutral heavy vector boson, which came from theories of Weinberg and Salam. Now, obviously, okay, people were looking for these particles, okay, if they exist. So searches were made for these particles. A good place to look for heavy leptons was in electron-positron colliders, and this was started mainly in the Italian labs, and this was then taken over later on in US and Germany. And a good place to look for neutral vector boson was coupled to weak interaction was an experiment with neutrino beams. Now, the idea of neutrino beam was first proposed by a scientist called Bruno Pontecorvo, and it was taken up by Melvin Schwartz. Bruno Pontecorvo obviously was an Italian, but he migrated to Soviet Union, and he wrote his papers through there. And Melvin Schwartz is an American physicist, and he pushed these things in the Brookhaven National Laboratory. And obviously, these things beams were showed that they found out there are two types of neutrinos. Okay, one was a neutrinos coming from the sun, which is a electron type coming from the also seen, okay, and the other thing which comes from a neutron decay, okay, the neutrino comes from there, okay, is electron type. And the other things come from the decays of the pions and kaons, okay, this is a muon, associated with the muon things, okay, it's a muon neutrino. Now, an intense neutrino beam was created using in the magnetic horn technique was discovered at CERN. So that was one thing, but then you have to detect those neutrino interactions. So they thought about having a heavy liquid bubble chamber was first built by Colin Ram. Okay, he built a 1.2 meter heavy liquid bubble chamber, and they said that, okay, using the heavy liquid bubble chamber, one could see a handful of these neutrino interactions in that. So this was a small bubble chamber. So obviously, okay, it was not good enough, okay, to observe large number of neutrino interactions. So a French physicist, whose picture is here, André Lagaric from Orsay, he proposed a second generation large bubble chamber called Gargamel. This was conceived in 1963. It was built and installed at CERN in 1970, and the first run was taken of the beam in 1971. And here I have a picture of Lagaric and the picture of the Gargamel bubble chamber. Not only he first devised the detector, he also made a first European collaboration, having a large collaboration to make this observation possible. So this was the first big collaboration, first international collaboration of physicists from Germany, from Belgium, from France, Italy, UK, and CERN. So this is the first big collaboration which was made by him. Okay, so that really took the next phase of the experimentation in high energy physics. So what they see, first of all, look, if you look for neutrinos with a what you call a neutral heavy lepton, obviously you have to have the neutrinos will interact and will produce interactions, a final state with no muons. Neutrinos, when interact and give a muon, obviously it will be a charge current interaction. But if it is a muonless event, is something which was there. But whenever you have a beam, okay, you have to think about what are the backgrounds would be there. Whenever you have a neutrino beam, there will be neutron beam will be there as a background. But the main difference between neutrons and neutrinos is that neutron is a strongly interacting particle, so it has a large cross section, and neutrino is a weakly interacting particle, so it has got a very small probability of interacting. So what happens is that most of the neutrons, okay, when it will be there, okay, they will interact mostly in the front part of the chamber. So if one tries to put a energy threshold of about 1 GeV and look at the distribution of the interaction point where the interaction has taken place, you see that those interactions has taken place mostly uniformly in the chamber. That means it's not a strongly falling things as a function of position. So looking at that, they said, okay, I mean, there must be something, okay, which is a neutron-induced background, okay, would be a diagram like what you have there, okay. This is a measured neutron stars with the energies below about a GeV. And they have a Monte Carlo, which was done at that time. Okay, I mean, they showed, okay, how the neutrons will interact. Okay, they said that, I mean, we could explain away the neutron stars, but a flat distribution will say, okay, this is a neutrinos which is interacting and doing that. But in addition to that, they observed an electron of high energy for doing that. Now, a neutrinos coming from muon decays, okay, producing electrons, that cannot take place, okay, without the exchange of a neutral current. And that really clinched the issue that you have the background for such a high energy electron is almost zero. So even a single event of observation of a single event with almost zero background, okay, I mean, that rules out, can create, okay, give an evidence of the neutral current. So that was the thing which, as a student, okay, I mean, that was the thing, okay, which I heard the discovery of neutral current, and afterwards, okay, I mean, Salam, Weinberg, and Glashow got a Nobel Prize after that. Unlucky, the gentleman Lagaric, okay, I mean, he died quickly after this experiment, so there was no experimenter could get a Nobel Prize. His effort, okay, really revealed that the Weinberg-Salam model is a good theory. But my second year as a student, okay, I mean, we saw the so-called the 70s revolution. So in October 74, two experiments at Brookhaven and SLAC came up with the observation of a very narrow state with a mass of 3.1 GeV. The Brookhaven experiment was done under the leadership of Samuel Ting, and he was using a dual arm spectrometer with 30 GeV protons hitting a beryllium target. And he was measuring the momenta of the electrons and positrons in this spectrometer, and he's observed a peak of which has got a width of about a few hundred keV at a mass of a 3.1 GeV. And normally, okay, when we have been seeing lots of resonances in those days, but the resonances all have a much larger width. I mean, this narrow width is something, okay, which was something, and at the same time, the E plus E minus collider at SLAC, under the leadership of Bart Richter, he was measuring the cross-section of this E plus E minus collision, and he saw the cross-section was spikes up at the same mass at the 3.1 GeV in all final states. When the final states are hadrons, final states are electrons, but positrons, or final states are pair of muons. These two experiments, okay, obviously saw a resonance, which is a pretty heavy resonance at 3.1 GeV with a very narrow width. Now, to explain away the narrow width of this particular state, one has to go back and tries to look at if there is a resonance called a phi meson, which has a narrow width, but not as narrow as that, which was going to pair of kaons for being there. And the mass of this phi meson was just above the threshold of this the thing, and so the phi meson was thought about buildup of strange quark and anti-strange quark. And K mesons have got a strange quark in it. So obviously, the natural decay of something which is a bound state of the strange quarks will naturally decay to something which will be carrying the bare strangeness. Now, the width was narrow mainly because it was the threshold effect of that. Now, somehow, if the mass of the something which is below the mass of this two bare quarks, okay, which was inside this new resonance, is above the mass of the new particle which was seen, then obviously we will see very narrow resonance, very narrow width. And that was said, okay, we came up, I mean, after this particular discovery, we saw hundreds and maybe thousands of papers, theory papers which came up. But the thing at the very end, okay, which really lasted, that we are seeing a new quark, which is called a charm quark. Now, obviously, we have to see, okay, the open charm final states. But the same experiment which observed the JSI particle in Stanford laboratory, they found the evidence of this new particle. But my first postdoc at Imperial College, we also tried to look for this thing in proton and proton collision, but we had no luck for doing that. We observed some, what do you call, a very narrow state, okay, but which was seen that is a statistical fluctuation later on. So we are really unlucky for doing that. But my first, what do you call, excitement of doing a frontline experiment started with this. Okay. So the next thing, okay, which was something which was an exciting thing for me was something which was called scaling. So during the late 60s, deep inelastic scattering of electrons on protons demonstrate that the cross-section depends only on some dimensionless quantity and not on the energy scale. This was termed as Bjorken's scaling and led to the idea of partons as point-like constituents of protons and all hadrons. Okay, this I have talked about in the past. Now, with the advent of high-energy neutrino beams from the SPS, several experiments were proposed at CERN West Area Experimental Facility to study the goodness of the scaling hypothesis. Now, two experiments which done, I mean, the thing is that neutrinos have very low cross sections. So obviously, I mean, we can build up experiments in line, okay, with the neutrino beam. It will first cross the first experiment, it will cross the second experiment, it will cross the third experiment, and fourth experiment. There are 4 experiments were done one after the other. The first experiment was all the four experiments were done at the same time. Now, the first experiment was called, is a big European bubble chamber. And the gentleman who was one of the leaders of this experiment was Don Perkins, whose picture is here. The second experiment was done under the leadership was Jack Steinberger. It was called this CDHS collaboration, which was in the second line. The third and fourth experiment, which was done after that. Now, the thing is, okay, I mean, this big European bubble chamber was using, it is a huge chamber. This is a 3.7 meter in diameter, and it was using a fisheye optics. Now, the main thing is that whenever a bubble chamber pictures are taken and with a fisheye optics, okay, the pictures are really very complicated. You can see, okay, I mean, you have to reconstruct this. You take a picture not using one camera, but with several cameras. Usually for waves, you are using 4 cameras. And from the cameras, okay, I mean, you take these pictures, you try to reconstruct them in 3 dimensions. Now, when we are trying to do in the 3 dimension, okay, I mean, could not really do in an automatic measuring machine. And when we try to use in a manual measuring machine with a fairly good degree of precision, we are finding that when you are trying to reconstruct them in 3 dimensions, we are failing. We have usually a pass rate of something like about 15 to 20%. And we have to, using this 15 to 20% pass rate, we have to really go up to more than 90% pass rate to have a realistic measurement. So we have to need a new way of measuring the events from these films. So what was done, okay, at that time, I mean, this was something which was assigned to me. You can see, okay, I mean, this was only, I would say, I mean, this is my first postdoc anyway at Imperial College. So we had to, at that time, the computers were not very huge, but this 3D reconstruction really requires, okay, I mean, nearly a megabyte type of memory, which was very difficult to have, okay, in a things of that size. Okay, it was a few hundred kilobytes of memory. Whereas, okay, I mean, we have to do these machines, okay, I mean, where we are doing this machine, semi-automatic measuring machines, okay, we have to really utilize programs, okay, which are for doing that, okay, where you can have at most a kilobyte of memory for doing the measurements. So if you are trying to measure, okay, I mean, 3 or 4 different machines, so we have to split the measurements were done using this measuring program at the level of a kilobyte, and it was collecting these measurements, throwing its measurements to the reconstruction program of a few hundred kilobytes, and then it gets the reconstruction done and gets its feedback done through this measuring program, and then it can go and proceed through that. So using this back and forth way of doing these measurements, we could really make a realistic measurements of these particular films. So this was the task which was given to me, okay, by my boss, okay, when he was my thesis guide, and I could give a name, okay, I mean, the name of my favorite, she was I do not know, I mean, a famous gymnast at that time was called Olga Korbut from Soviet Union. So I could name the program as Olga, Online Geometry Analysis. So whenever the measurer was measuring on the things, okay, I mean, and trying to send the things, okay, for the big program to say, okay, I mean, they're saying, okay, I mean, it used to write a thing that Olga is working on it. And then I think Olga gives the feedback to the measurer, and then obviously, okay, the measurement proceeds. So when I was leaving Imperial College at that time, I had to leave, okay, because I wanted to come back to India. I got a, what do you call it, all the measurers, okay, I mean, they used to, I think I got a love from them, because there were three groups of measurers, okay, one was starting at 8 o'clock in the morning, the second group starts at 4 o'clock in the afternoon, and third group starts at 12 o'clock in the night. And I used to attend all the three groups, okay, at that time, okay. So I used to come at 7 o'clock in the morning, and I used to go back at 3 o'clock in the morning, okay, for the next thing. And I used to sit with them, okay, for these things, okay, for all the three shifts. So I got my most memorable prize in my life. It was a brooch saying Olga is not human. So I really loved that prize, okay. I mean, that was the biggest prize I would say, okay, which I got from the measures at that time. Now, these particular experiments measure the structured functions over a large range of energy transfer, and it demonstrated clear violation of this Bjorken scaling. And not only this scaling is violated, it also said that this was a logarithmic violation. And this was the first quantitative evidence of the quantum chromodynamics. So this was definitely one of the, I would say, one of the big experiments in which I could say, okay, I mean, I had made some contributions. Now, I'll move to another thing which is called jet physics with gluons. During the early 80s, okay, I mean, we had this, late 70s and early 80s, okay, we had E plus E minus collisions in both in Stanford and in DAISY in Germany. And first of all, they saw that you have got in E plus E minus collisions, okay, the hadrons which are come out, you have hadrons come out, they comes in the forms of jets. That means E plus E minus goes to a quark antiquark, and the quark and antiquark obviously dress themselves in hadrons, but these hadrons come more or less in the direction of the patterns which comes out. Now, normally, okay, we have a E plus E minus goes to quark and antiquark, okay, we should have only two jets which will be coming out. But the thing is that in these experiments, they found out, okay, there are three jets are coming out at some rates. And this was essentially came from an experiment done by a group of American and what do you call it? It's an experiment called TASO. And the two persons who were mainly leading these experiments was Saulan and Bjorn Wick. And this was a discovery of the gluons, which was the glues the quarks and antiquarks together. Now, the thing is that, okay, I mean, I was at that time was participating in another experiment called Cello. I mean, obviously we also saw this type of things, but that was not the main thing. But what we saw later on is that when you try to look at these experiments, we also could measure the strong coupling constants for doing that. And we measure the strong coupling constant as a function of energy. And this thing which you try to do this measurement of the strong coupling constant as a function of energies over a large range of energies, and we saw that strong coupling constant falls when the energy increases. This is a signature of asymptotic freedom. And obviously, okay, this was the evidence of asymptotic freedom for strong interaction. This came from a group of E plus E minus experiments and obviously, okay, I mean, I would say, okay, I mean, the guys, okay, who made this theory, okay, for this asymptotic freedom, okay, I mean, you have, they got the Nobel Prize out of it, okay, the theoreticians obviously get the Nobel Prize out of it. So this is my contribution, okay, in finding this experimental proof of the asymptotic freedom. Now, the thing is, okay, I mean, I have not talked about, okay, I mean, so far about anything about the Higgs boson. But Higgs bosons was not, I'm so far talking about quarks and leptons, which was really building up the theory of high energy physics, theory of strong electromagnetic and weak interactions in high energy physics. Now, the CERN came up with the idea of a large ring as a collider of electrons and positrons. They came up with the idea of finding the W's and G's using these things in the mid-70s. But to make this particular collider, it took a long time. Okay, it could be completed only in the late 80s. And obviously by that time, okay, the W's and G's were discovered by proton-antiproton collider by Carlo Rubbia. So this particular collider, which was built, okay, was trying to measure, okay, essentially the properties of these Z bosons and W bosons with a very high degree of precision. And there was an experiment called L3, which was led by Sam Ting, in which the TIFR group was a participant. And this was a detector which was built, okay, for doing this particular thing. And since it did not have a chance, okay, to discover W's and Z's, okay, they tried to make very precise measurements of the properties of the Z bosons and also of W bosons. So with these measurements, they tried to rule several things. Okay, they found out that the number of light neutrino species was only 3. They found out that the radiative corrections are determined with a significance of bigger than 5 sigma. Obviously, that particular thing, okay, said that the radiative corrections are important, and that gave, okay, I mean, Veltman and Tuft their Nobel Prize. And obviously, this also experiment said that top quark mass would be between 170 to 185 GeV. So that was the thing which was essentially came out from this experiment. Now, so with this thing in mind, okay, I mean, we have got the zoo of particles, which has got 3 families of quarks and leptons. And the quarks comes in 3 families, and each family has got 3 colors. And again, the evidence of the 3 colors, okay, came from the E plus E minus collision experiments. I'm not talking about that. Okay, I mean, and this is the zoo of particles. So this was the zoo of particles was complete, but there was only one thing was missing. Okay, I mean, the standard model was good when all these quarks and leptons have 0 mass. So how you can introduce the mass of these particles? As soon as you introduce a mass of these particles by hand, it breaks down the theory at high energies. So you said, okay, I mean, a theory is good only when it is good at high energy as well. So theorist has to think about some ways of trying to introduce some ideas for doing that. And that idea came from an idea from condensed matter physics due to Anderson. But in high energy physics, this was done by a group of 6 guys whose pictures are here. They are respectively from left to right is Grundig, Hagen, Kibble, Peter Higgs, Engler, and Brout. Now, I think the first idea of this thing came from the theory. The 2 papers was the Engler Brout from and also by Peter Higgs. Now, that was applicable in one class of theories, which was not quite the theories, which was so relevant for that. But that was the first ideas. That was much better done by the second group of people who were these 3 guys. Gulden, Hagen, and Kibble for doing that. Anyway, these six guys who really brought out these particular ideas. So they said, they have some symmetries which are spontaneously broken, and this spontaneous breakdown of this symmetry will bring out the mass of this particle without really breaking down the high energy behavior of this thing. So this really completes the whole theory. And as a matter of fact, with this and Tooft and Weltman really worked out that, with that, they can really make the theory of weak interactions to be really good. Now, apart from this, this particular theory said that every new particle which would be required, and this suggested, the new particle was suggested by, though the mechanism was suggested by all this thing, but this thing will introduce a new particle was essentially came from the paper of Peter Higgs. So that's why we call it Higgs boson. Now, the thing is, now, what this particular theory is there. So the theory is good, but it does not say, how to look for an object of this thing. Now, if you have a chance of look for such an object, so say for example, if you find a person of some properties, but with no address in a big cities, how would you try to find it out? So obviously, it's almost an impossible task, to find such a thing. And particularly if the cities is huge, and you have got millions and billions of addresses in there, it is almost something which is an impossible task for doing that. The first thing was done by through the work of this gentleman, Tooft and Weltman. They said, as I said, I talked about this radiative correction. So they said, the higher order this particle can have an effect on the interaction probability of an observer for doing that. For example, before the discovery of the top quark, we looked at this E plus E minus going to E plus E minus, or E plus E minus going to hadrons. But there is a contribution of the top quark in the cross section itself. And that really restricted the whatever the cross section would be. So whenever we try to measure the cross sections, and we are trying to say that this yellow band you are seeing here is the mass range in which the top quark mass would be. So you can see that with a more and more precise measurement, obviously you are getting a precise knowledge of this thing, and you were trying to see, okay, what exactly, okay, the top quark mass would be. And finally, okay, when you end up with a region, as I said, okay, where exactly the top quark was eventually discovered in the Fermilab collider. Similarly, okay, I mean, obviously, okay, I mean, Higgs is also there in this particular cross section. So one can try to see, okay, I mean, how the Higgs mass would be, okay, but the dependence of the top quark mass was a quadratic dependence, but the Higgs was a logarithmic dependence. So obviously, okay, I mean, we do not get such a precise measurement of the restriction of this thing, but we are trying to get a closeness of this thing. Okay, we are getting somewhere between 200, below 200 GeV. So that was one thing which was there. So that was the first hint, okay, where one can take a look, okay, I mean, where to look for this Higgs boson. Now, so all this precise measurement, okay, obviously could not be seen before the LEP experiment. The LEP experiment was the first place where a direct evidence of the direct search of Higgs boson was first made, and it was looked at all the places where Higgs boson could be seen at up to an energy of mass of 114 GeV, and it was not seen up to 114 GeV. So LEP experiments ruled out Higgs bosons of masses below 114 GeV. So before the LEP experiments, there was no real experiments which could have any hint of direct observation of the Higgs bosons. There was a no, I'm not talking about that. Now the thing is, okay, I mean, so how to find the Higgs boson? So it has to be produced in interactions. So you collide particles with sufficient high energies. So protons are a good choice for colliding particles. The probability of Higgs production is small, so you need a large number of interactions. And then you have to see how the Higgs bosons decays. Again, okay, I mean, you look at the Higgs boson decays, and the decays properties depends on the mass of the Higgs boson. If it is a low mass Higgs, obviously it has to be decayed into a pair of quarks which has got a mass of the below the things. Okay, so if it is above 10 GeV, okay, it will 10 GeV or above, it will decay mostly in the BB bar quark. And so obviously, okay, I mean, it will dominantly, okay, I mean, if it is a thing, okay, it will dominant decay mode is a hadrons with a BB bar quark in the final state. Now, if you these two persons, okay, I mean, John Ellis and Marie Gaillard, they investigated these things in great detail to look at these cross sections and on these things, okay, and at the very end of it, okay, they said, okay, I mean, this is a thing to look, but I think most likely you would not be able to. They said they discourage the experimenters not to look for Higgs boson because it's so difficult to look for it. So that was the main conclusion for that. I mean, this is a way to look for it, but it is so difficult that it is almost impossible to find it. So that was the conclusion essentially from Ellis and Gaillard. But they give all the hints, okay, how to look for it. So obviously, okay, we came to this high energy collision. So we have to go for this large hadron collider. So the same ring where these electrons and positrons were colliding, okay, the same tunnel was used, okay, where instead of accelerating electrons and positrons, they're accelerating protons, and the protons were coming in opposite directions, and they're colliding at certain points. And that was the thing, okay, where they built up 4 experiments at that time. The 2 experiments were general purpose experiments. One was called Atlas, the other was called CMS. They are general purpose experiments and essentially trying to look for the Higgs boson. And there were 2 other experiments were trying to look for 2 specific things. One was look for heavy flavor type of experiments, the other looking for heavy, what you call, quark-gluon plasma. The Alice was looking for quark-gluon plasma, and LSCB was looking for the heavy flavors violation. Now, the protons are obviously were not coming from one accelerators. Okay, they have a chain of accelerators from which it was there. So it was starting from a LINAC, linear accelerators, where you first of all ionize the hydrogens, okay, to get the protons, okay, and then you accelerate this protons, and then you put them into a booster. From the booster, you get it to a certain energy. Then you put into a proton synchrotron. It is energized further. Then you put into a superproton synchrotron, where it is energized to about 450 GeV, and then you inject into the LHC tunnel, where it was accelerated further, okay, to go to 50 EVs, okay, where the protons were eventually colliding. Now, how many protons which were there? You can see, okay, they have got 2 times 10 to the power 12 protons per beam, and we have got few thousand some bunches in the thing, and these bunches were colliding at the bunch collisions were happening at a rate of 40 megahertz. So obviously, okay, I mean, you have to have detectors which are very fast, and obviously it has to be very much resistant, okay, to what do you call radiation hard, and it can tries to take a look at these things, okay, I mean, at the highest possible what do you call the granularity. Now, what makes an LHC? It contains beams in the LHC. We have got 1232 dipole magnets, which are 15 meters long and providing about 8.3 Tesla and having a current, a very high current itself. So you need superconducting magnets at liquid helium temperature. We have got also focus these beams, so you need quadruples and other sextuple magnets, okay, I mean, which are several meters long. And obviously we have got radio frequency accelerators, which are operating at 4.8 megawatt. So few facts about this LHC, okay. The energy stored in the magnets is about 11 gigajoules. This is basically the Airbus 380 at a cruise speed of 700 km per hour, and it can heat and melt about 12 tons of copper. So that is the amount of energy stored in that. The energy stored in a single beam is about 360 megajoules. Is equivalent to 90 kilogram of TNT or 16 kilogram of chocolate. The amount of liquid helium in the machine is about 60 tons or 120,000 gallons. LHC is the coldest place in the solar system at a temperature about 1.9 degree Kelvin, and it is also the emptiest space in the thing where vacuum of the pipe pertaining. I mean, it's the emptiest space in the universe. So, what was the camera? The modern camera is called a detector which was built by a group of few thousand people from all over the world, and it is called compact neon solenoid. The compactness is said that it was a diameter of 15 meters with a length of about 28.7 meters and a total weight of about 15 megatons. So this is a picture where you have a detectors which starts with a detecting the trajectories of charged particles using silicon detectors. Then the neutral particles are detected in calorimeters. For example, the electrons and photons are detected in a what you call an electromagnetic calorimeter, because the cross sections of these electrons and photons is extremely high in the level of bands, and the hadrons, both neutrals, hadrons and the charged hadrons are detected in the hadron calorimeter. So all the hadrons, electrons and photons are killed in the calorimeters themselves. So the things which left out are the muons and the neutrinos. Obviously the neutrinos are never detected in our detector, but the muons are detected in the detectors which is outside, which is called the muon chambers. So this is our camera. And the few facts of the CMS. Okay, I mean, CMS is the heaviest particle physics detector on the Earth, and it is as heavy as the Eiffel Tower, but it is 800 times as dense as Eiffel Tower. The solenoid of CMS is the most powerful magnet of its kind ever built. It generates magnetic field of which is what you call 100,000 times stronger than the field, the Earth's magnetic field, and it can melt about 18 tons of gold. The tracker is built out of silicons, and if you really stretch all the silicons, okay, I mean, it will cover, okay, I mean, a tennis field, okay, I mean, and it has got a connection of about 6,000 connections per centimeter square. The electromagnetic calorimeter contains 86% metal that is completely transparent. The observer of the hadron calorimeter uses brass which came out from the million cells in the Russian Navy, okay, in the Second World War. So this is how a particle is detected. So when a particle comes out, obviously it traces its things in the tracking detector if it's a charged particle. Then the electrons and the electrons and photons, okay, they'll detect, are absorbed in this electromagnetic calorimeter, and they are completely absorbed in the electromagnetic calorimeter. The hadrons starts showering in the electromagnetic calorimeter, but they are totally absorbed in the hadron calorimeter, and that leaves out the muons, okay, which leaves out in the muon chamber, and neutrinos are undetected. So when you measure the total energies, okay, I mean, obviously, okay, I mean, the missing energy, okay, is essentially due to the neutrinos or something, okay, which is weakly interacting and not. Now, the thing is, okay, the LHC was a really successful thing, okay, so they really was successful in providing this thing, okay, so it started with a low luminosity, that means its total number of interactions was very slow, very low. So the pictures was like this. So you can clearly see them coming out this thing. But with this interaction, like we can clearly find out, okay, what are the particles which are coming out. Okay, that is very good for identifying particles. But obviously, the number of what do you call interactions are very small, so you will not be able to see Higgs boson, okay, with this rate of interaction. So obviously, they have to increase the things, okay, and then they came up afterwards, okay, with more number of things, okay, and some becomes complicated, and eventually it came up with a picture like this. But so we have to really work with a situation like this, and we have to identify things in the state. So we have to first of all store these informations in disks. So we are getting something like 1500 terabyte of information per year. That means 15 petabyte per year. It is like recording a DVD every 4 seconds, and enough to fill your hard drive in 2 minutes. And processing is has to be done around the world. And we have to use what you call LHC computing grid for doing that. And if you really put all the things on the earth, okay, obviously, okay, you can see, okay, how much disk space, okay, how many disks, okay, that is the thing, okay, which will be there. Now, with such a complex detector, okay, I mean, obviously, the first thing you have to see that you have really trying to see that, believe what we are seeing. So we start seeing all the things which you know which exist. For example, we have to see the muons, we have to see the pions, we have to see the things which has already been discovered. And obviously you can see that all the particles which we're seeing, okay, in the 30s, 40s, 60s, 70s, 80s, 83s, I mean, like WZs, okay, I mean, this was seen only after, what do you call, you start having the things in few seconds after the things, and after we started in 2009, and in 2010 in June or July, okay, we see all these new particles. So obviously we are now convinced that what we are trying to see in our detector is right. So we can proceed, okay, and try to see something more. Then we start seeing something which we were very rare. We start seeing objects like, okay, we have two very high energetic photons which is coming out. You can see one photon is going in this direction, another photon is coming in this direction, and this is very high energetic photon. And if you reconstruct the masses, you are measuring the energies of these things very accurately, and if you reconstruct the mass, we get a mass around 125 GeV. Apart from that, we are also trying to see that things like 2 electrons, I mean E plus E minus and mu plus mu minus. And then obviously when you try to reconstruct their masses, we are coming up around 125 GeV. So we put all these things information together and we try to do a statistical analysis of that. And what we see that we are seeing the statistical significance of this thing from a standard model source. We're seeing that we are seeing an object at 125 GeV, which cannot be explained by anything, okay, which comes from a standard model physics. And this deviation is about a 5 sigma deviation. 5 sigma means, okay, the observations is a what do you call it? 1 in 10 to the power 5, 2 times in 10 to the power 5. So I think, okay, this is such a very rare thing, okay, which is seen. So we are seeing something which is a object. So obviously, okay, there was celebration thereafter. I think this has happened in 2012, that we have observing a Higgs boson, a Higgs boson-like thing, okay, at that time. And this was telecast in, what do you call it? Simultaneously shown at a CERN symposium, the CERN, what do you call it? Yeah, it was shown in a, and it was also telecast in Australia, where we have a ICHF conference at the same time. So these guys were in ICHF conference, and these guys are sitting in the CERN, and these are the speakers, okay, who are trying to speak from ATLAS and CMS experiment. So obviously, okay, this was a thing which was said in 2012, and obviously there was excitement in the media, and this was done on July 4, 2012, and obviously it was shown all over the world, okay, including India, and came up in all the papers all over the world. And obviously in October 6, 2013, okay, we have some more evidence of this observed particle, that we are seeing that this is really a scalar boson. And then you can say, okay, this is not just a boson, this is a scalar boson of spin zero particle. All the properties which this gentleman has predicted. This is Peter Higgs, and this is what is his name? Engler and Higgs, who come in there. They are present in that CERN symposium, and they got the Nobel Prize out of that. So that was the discovery of the Higgs boson. So the economists also came up with a summary, okay, that in 2012, 2 experiments operating at Large Hadron Collider provided a strong evidence of a new particle with a mass of around 25 to 126 GeV. The observed properties of the new particle are consistent with the things which was predicted by the Higgs mechanism. These studies who attention, I mean, the rest of the things are not very important, okay? So I think that was the thing, okay, at the time. So obviously, the thing which stands with to figure what happened next, okay? We are trying to measure the properties of this coupling of these Higgs bosons with the quarks and leptons, and obviously we can see a relationship with the mass of the quarks and leptons, okay, with the coupling constant, and these things are measured obviously with a precision of this. So obviously this is the precisions, okay, I mean, with which you measured in 2013 per se, I mean, or even the first half of 2015 or 2016. But this is not good enough. We need a precisions like this. So we keep on doing that, what happened to be next. So we have to, I think I better stop here, okay, I mean, at this stage. So we have to keep on doing this measurement, okay, I mean, I will stop here. We'll keep on trying to doing this measurement, and we're trying to go up to an accuracy which is far better than this, and we try to study the property of this Higgs boson to a better thing. And Higgs is a new object in this field, and we can utilize Higgs boson to probe to the properties of matter. So I'll stop here. You can.
Yeah, really mesmerizing session is going on, and we learned more than 50 years of history of what is going on in CERN, and I'm sure that the students learned a lot. And we have a few questions, and the first of them is from Peter from USA. I'm showing the question to the screen. Can you see the question?
Just a minute, okay. I mean, would you mute me on?
Yeah.
How can would a muon collider?
Help in finding the particles you mentioned, and if so, how?
Obviously, okay. Obviously, muon collider obviously will do exactly the same thing as a E plus E minus collider or a PP collider. I mean, as a matter of fact, okay, muon collider will have a less background than a PP collider because you have not so much of what you call hadrons which will be produced in that thing. But it has got muon collider has a background due to the muons are decays in the flight, and one really has to kill the neutrino. I mean the decays has to be carefully shielded in a muon collider so that you can have a very clean picture for doing that. So muon collider will be a to really study the properties of the Higgs boson in more details, you have to do a future high energy collider. Lepton collider are the best example. E plus E minus collider needs a much bigger circumference, whereas muon collider can easily fit inside Fermilab. But muon collider has to really work out to come in with the how to shield the special decays which comes because of the muons in flight, and there are clearly okay, I mean, what is called shielding studies which is there, and I think okay, I mean, if a muon collider is approved, it would be a cheaper option than a plus minus collider, and I think it would be a great thing, okay, at least for both either US or Europe to do it. I think US is, I mean, Formula can build it inside Formula itself, but several R&D things has to be done, okay, to make the muon beams, okay, and the shielding properties of the in the detector itself.
Yeah. There's a question from Devbata Sur. He's asking, is there any other subatomic particles left to be discovered? I guess yes, certainly yes, but yeah, your comments.
Look, I think the thing is, okay, I mean, standard model is an effective theory. Obviously, okay, what happens is that, okay, why you have a Higgs boson of mass of 125 GeV. Higgs boson, I think if you do not have, normally, okay, whenever there is a restrict the mass of a particle, there has to be symmetry, okay, which tries to restrict it. So obviously there should be some other symmetry which is there, okay, which restricts the mass of this Higgs boson to 125 GeV. And there are theories for doing that, but that needs discoveries of other particles. Now, so I think, okay, I mean, if those things are not discovered, obviously those theories are not valid.
Right.
And so till they are not discovered, okay, we cannot say, okay, these theories are good. But as I said, okay, standard model, as it says, okay, it is an effective theory, but it is not a complete theory. So you definitely need, okay, something beyond standard model for doing that, and that really needs, okay, something beyond what we saw in the particle zoo itself.
Yeah. So there's another question from Debrata Sur. He's asking, is there any relation that more the power of the collider, more the chance of discovering new subatomic particles?
So sorry, can you repeat the question again?
Yeah. He's asking, is there any relation that more the power of the collider, more the chance of discovering new subatomic particles? Probably he's asking that if you increase the energy, whether the chance of discovering more particle.
Yeah, I think obviously, okay, I mean, whatever things are discovered, okay, are using the energies which is available to us so far. So if you want to go to something more, okay, I mean, we have to really either go up in energy or come into up the accelerators for doing that. There are two ways of doing things. So I mean, either we have to have high energy accelerators. That means, okay, which are called discovery accelerators, or we have to make very high precision experiments by which you can try to see that certain things are violates some of the things, okay, which is there. For example, okay, I mean, the G-2 experiments of the muons, okay, I mean, these are the things, okay, I mean, are done with the precisions which is extremely high. Okay, I mean, and the deviations, okay, from standard model, okay, I mean, if it exists, okay, so far, okay, there are deviations at the level of about 3 to 4 sigmas. 3 to 4 sigmas is a strong deviation, but it's not a deviation which is clearly says, okay, this is wrong. If it goes beyond 5 sigmas, then I think, okay, I mean, obviously, because there's something definitely exists.
Then you told you about.
So that is another way of trying to discover things.
Yeah. There is a question from Krishnanjan. I'm showing the question here. He is asking if a standard model could not be completed without Higgs boson, then why still it fails to describe gravity?
Well, I think no. So far, standard model is a model, okay, to describe only 3 types of interactions. So I mean, it is gravity is a different thing altogether, and trying to build a theory, okay, which can try to what do you call it?
To bridge the other 3 forces with gravity.
Yeah, with gravity, okay, that is a hard thing to do, okay. I mean, and I think, okay, it really definitely needs, okay, I mean, a strong, what do you call it? Strong theoretical ideas, okay, for bringing them together. So far, okay, the standard quantum field theory, okay, for things for doing gravity is not really working out very well. There are attempts for doing that, okay, but it's not really can be brought in the same areas, okay, but the other 3 interactions can be explained.
Yeah. There's a question from Avijit Laha. He is asking that is it possible to test string theory in CERN? I guess no, but your comments.
Look, this is a thing, okay. I asked, well, not I, but several people asked Ashok, okay, I mean, you know Ashok Sen, okay. What is a thing of which can disprove a string theory? Any experimental observation which can disprove a string theory? He does not
There's
find
nothing like that. Yeah.
he does not say anything which can disprove a string theory. if we can say, okay, I mean, this can disprove a string theory. Obviously, okay, I mean, anything which we see in, okay, it can be, string theory can explain that. So he can try to provide things which can disprove a string theory. For example, if a neutral current was not seen, that will disprove Weinberg-Sananda model. So
Yeah, the other way also, you don't have anything which proves string theory. And, yeah,
you
so
cannot,
yeah, you cannot.
you have to say something which this is
Yeah,
observation of something which can disprove
yeah.
string theory. Then obviously
Prove
we
or
can.
disprove. Yeah. So string theory is a nice theory on paper, but so far we have nothing. We have no way to prove or disprove it.
It is a philosophy, I would say. It is not a
It's
it is not a physics.
it's totally
To me, it's
yeah.
not a physics. A physics is something which can be proved or disproved.
Yeah. Right. So
It's like,
string theory is it's a it's a beautiful mathematics. Actually, yeah. Actually, I kind of tried to start my career with string theory, and I spent one and a half year time at the beginning of my career, and then I found that it's too much mathematics, and it takes for some of its equation, it takes two double column one page of an article, whole two columns takes just to write one equation. Then I thought that okay, it cannot be the language of nature. So for nature, all the equation, it has to be simplistic. Means you can take 30 pages to come at a equation, but at the end, all the equation is simple. So string theory, it's a beautiful mathematics, but so far we have nothing to prove or disprove, I guess.
yeah, I think, okay, I mean, if it has something to disprove it, I mean, then I think, okay, obviously, okay, we can try to do some try to think about experiment for doing that.
Yeah. So we have some comments from Sananda Madam. So she's showing her respect to you, and she has some questions for you. She's asking that what kind of difficulties you faced probably in the earlier times in comparison to the present time, and she's asking for some advice to our youth.
Well, the only thing I must say is that I think the difficulties will be there at all times, all the time. So first of all, okay, when we started doing experiments in India, we had almost zero support, okay, from the government, almost zero support. So when we first went to do the experiment at CERN, okay, I mean, people did not really think that we'd be able to contribute to it. And we were really struggling, and we had almost got no money, okay, from building the experiment. And obviously only at being at TIFR, okay, it helped because TIFR has certain money, okay, from their non-planned budget, from which you can do certain things. And we got help by borrowing things, and which we obviously, when we borrowed things, okay, we did not pay it back. We borrowed things from the NPC in terms of iron. We borrowed things from VRC, where we built part of the things in the workshop, where we did not have to pay for the making the things in the workshop. And so all these connections really helped us for doing that. And obviously, when we have to contribute in the form of support, we have to be present at CERN, okay, for doing this experiment. And we got help from the CERN itself, okay, for support of the students. They paid certain amount of money, and normally whatever they paid, okay, for one person, we have to split that thing into three persons. So obviously these guys, okay, really have to struggle, okay, for living there, okay, with very limited amount of budget, okay, and they try to work out, okay, and each of them, okay, for example, I said, okay, I used to work, for example, I said, okay, during one time I started my work at 7 o'clock in the morning and worked till 2 o'clock in the morning. These guys also did the same thing, okay, for certain amount of people. The only thing which kept us alive was the love for the work. And I really loved my experiments, okay, I mean, and I still love my experiment so far. So that is the thing, okay, which really drives us, okay, for doing that. So I think, okay, whatever you do, okay, I mean, you may not get anything back out of it. You get the only satisfaction that you have worked on it, and that can only the thing which can drive you. You may not get any other things out of it apart from these satisfactions.
Yeah, and the satisfaction keeps us living. So we are all doing things because we love to do that. Yeah.
Yeah, I think this is true for almost all the people. Okay, I mean, yeah,
Yeah,
who are doing such in all branches of science.
Yeah, and I guess we are lucky people because we are doing what we love to do. So and not many people get that opportunity. So we scientists who are attached with science, we are kind of lucky people. Yeah. So it's been almost 2 hours, and we have to stop here. So I guess our students they learned a lot from the really great lecture from Sananda sir, and I thank Sananda Babu for this nice lecture, and we'll hope that we in future also we'll have opportunity to learn more from him. So with this, we are stopping to the good night to everyone.
Yeah, and anybody can contact me over the email. Okay, I mean, so if you know my email address, okay, I mean, you can forward my email address to anybody.
Yeah. Thank you, sir.